Hey class, and welcome to part 4 of Building Envelopes and HVAC. This time we'll be covering infiltration. So a quick overview of HVAC, heating, ventilation, cooling. Uh, we need to supply fresh air into a building and exhaust some of the stale air. Everybody sneezes and exhales, all that good stuff is in here. We want to exhaust a lot of that. That's our return air that's coming out. And some of our return air gets exhausted out. This is our exhaust air. But because we want to save a lot of the energy inherent in that airstream, because we've spent a lot of time heating it up or cooling it down, we end up recycling a lot of that. So our return air gets mixed through a damper with a certain amount of outdoor air. And then we blow in that outdoor air and supply it to our building. And one thing to note is that when the HVAC system is on, when it's doing heating or cooling or even just providing ventilation, generally the supply air is at a higher pressure than the return air. So our building is overpressurized usually. So if you open up a door or a window, you should actually be able to feel some of that air kind of pushing out a little bit against you as you walk into the space. And this is really to help reduce infiltration, because if it was under pressurized, right, all that outdoor air would be trying to find its way into the building, causing really cold or hot spots within the space. And infiltration impacts the HVAC loads quite a bit. It can be up to 30% or more of total heating loads, whereas it can actually save a little bit on total cooling loads. Now, this depends a lot on building and climate. These numbers are based on a nationwide study of commercial office buildings. But those are the HVAC loads, not necessarily the energy use in the building. If you're looking more holistically at the total energy use in a building, infiltration accounts for up to 6%. Now, that's still a pretty big number. If we can reduce that, then we can definitely see some savings from just a purely financial perspective. All right, so how do we actually measure it in terms of units? There's two main ways. There's a couple others, but I'll just focus on two. First is you can look at the CFM, cubic feet per minute, per square foot of the building exterior, right? So you have to add up all the surface areas. This includes walls, windows, doors, all of that. Look at the total square footage. And if the building is pressurized at 75 pascals, they use like a huge set of fans to do that, then you want to keep that CFM, the volume of air escaping out at a minimum. The other is looking at the entire building and trying to limit the number of air changes per hour that occur at a slightly lower pressure, 50 pascals. And sometimes that's used by the passive house standard. All right, but it's kind of hard to equate these two, right? This is general code requirements. Once again, IACC 2015, what we see in Idaho for commercial buildings. You want to keep your CFM per foot squared below 0.4 when the building is pressurized to 75 pascals or 0.3 inches of water gauge. The 3 air changes per hour at 50 pascals is approximately equal to this, assuming a 5,000 square foot building with 10-foot ceilings, right? Because the air change per hour really depends on the building volume. So generally, ignore the ACH and just stick with the CFM per foot squared. Now, when a building is constructed, it can go through a big testing where it is pressurized and they actually commission or measure this CFM per foot squared. But oftentimes it's not. I would say this is hardly ever used. Usually, what is used in commercial buildings is a prescriptive approach where you're looking at individual components. Each wall, each air barrier that you're putting up has to have a certain amount of resistance to infiltration. It's very rare to have the whole building commissioned and looked at from an infiltration perspective unless it's trying to achieve something like the passive house standard. So that means a lot of things can be missed within the building. And little gaps can show up within construction and have a really big impact on the energy use of that building over time. There are three tools that you can use to identify points of air coming into the building and causing excess energy usage. First is your trusty IR camera. Make sure it's kind of calibrated and really focus it on a particular area within the building. The second is a smoke pen. I've got one of those here. I can open it up. It's basically a fancy, well, a less fancy version of incense. It has a long wick that you light with a set of matches. I often forget to bring these when I'm going on a building audit. I'm not a regular smoker, but I'll go ahead and light this up. And what it does is it basically produces a little cloud of smoke. Here, let me just pause right now. I won't insult you with watching me try to strike a match. All right, now not a whole lot of smoke is coming off of this, and it's a white background, so it might be a bit hard to see. But the idea is you basically get a cloud of smoke and you watch it waft through a building. If you are worried about setting off smoke alarms, I've never had one go off when I've used one of these because it's from kind of a special material. But even if so, you can use a little bit of baby powder. And I like to do that around windows as well as elevator shafts and just shake a little bit out. It's not as easy to see as the smoke pen, which really does have a high buoyancy and it floats through the air very nicely. The baby powder does really fall a lot, but you can still see it kind of start to drift towards certain areas. The other tool that you can use is a carbon dioxide sensor. Now, I wouldn't recommend using it for like full commissioning. It can be really tough to get a calibrated gas mixture. But if you are doing an energy audit, I like to set up a carbon dioxide sensor or two just to get a sense of what the CO2 level is like. And if it is, say, way higher than 400 parts per million, then you know that maybe the ventilation system isn't working properly. Or if it's staying at 400 even, then they might be over-ventilating the space, right? Better to be over-ventilated than under-ventilated for those of us that like to breathe. All right, so just a couple of images here. It's really nice to be able to take pictures very close up, as I was saying, where you can see kind of some of the air drifting through, and use a smoke pen as well to look at, gaps around windows and the like. So where should you be pointing that camera or taking the smoke pen? Windows, right? The caulking around the edges, the seals can wear out over time. Corners of buildings, recessed lights are a big one. Roof to wall connections, as well as any penetration through the building, electrical conduits, your gas line coming in, even your HVAC ducts if they're not properly sealed around, right? Because you're bringing conditioned air down through the middle of the metal tube, but if you haven't, added any insulation around the outside, you still might be getting some outdoor air in. All right, let me pause just a minute and switch screens. All right, so a couple of resources that I found particularly helpful is the air leakage guide. If you just look up energy.gov and Google air leakage guide from Department of Energy, it's mostly focused on residential, but it really highlights different areas to look in a building for infiltration. Another resource is this source here from Lee Durston. Once again, just Google design, construction, and testing of the commercial air barrier. He's a building scientist, and want to show you guys a few images. So these are some of the fans. Let me switch to full screen mode. That are used for doing one of those pressurized tests that might be beyond the scope of IAC, but if you ever get the chance, they're great. Let's see, and go down to the next page. So he really notes the importance of having a finely tuned camera specifically focused on small areas at a time, so you get a very narrow temperature range to really highlight areas of infiltration. And what you want to be looking for are basically these streaks, if you will, where air is actually coming through. And he likes to run it on a depressurized building, if possible. So you're basically reversing the airflow and trying to exhaust more and pull air in, the opposite of what a building's normally doing, but it really highlights points of infiltration if the building operator is willing to do that. So here you can see some infiltration that's happening around the insulation that's been pinned to a masonry wall construction. If you look here where they removed the drop ceiling, there was some warm air coming down through the attic. Here, you know, more air kind of coming through the windowsill. Recessed lights, like I said, here you can really see the streaks. As the air is passing over that surface, it's really starting to change that surface temperature. Makes it much easier to see that that's due to air and not necessarily thermal bridging coming around this recessed lighting that hasn't been properly sealed off from the plenum that's above it. Same here, air infiltrating kind of at the base of a wall, as well as air coming up above this curtain wall here, once again looking at that roof to wall connection. More air kind of coming through at the corner here, and especially focused on penetrations through the wall that might have otherwise been missed in construction. And you know, you can back these up using a smoke pen or a smoke machine to really get another visual sense of how the air is actually being sucked into or out of the building. So I hope that gives you a good sense of infiltration and ways to spot it, some of the energy impacts. I look forward to seeing you guys next time.